I'm Jamin Nilsson. This is my top 10 pick list of the greatest accomplishments NASA made during the Apollo space program.
During America's first human spaceflight program, Project Mercury, the eyes of the world often focused on the launch pads at Cape Canaveral Air Force Station in Florida.
5, 4, 3, 2, 1. Lift off. All right, lift off and the clock is turning. This is Philip Point. The fuel is go. Oxygen is go.
Another centerpiece facility for astronaut training, crew quarters, and spacecraft processing was Hangar S at the Cape. While not as well known as the Mercury Control Center and the launch pads, Hangar S was the location of crucial work supporting NASA's early human spaceflights. After the National Aeronautics and Space Administration was formed in 1958, the new agency announced the selection of 7 military test pilots who would become America's first astronauts. Scott Carpenter, Gordon Cooper, John Glenn, Gus Grissom, Wally Schirra, Alan Shepard, and Deke Slayton would soon become household names. From 1959 to 1963, the 61,300 square foot Hangar S became a hub of activity as America prepared for the program to send men on their first trips into space. Hangar S was built in 1957. It housed operations of the U.S. Naval Research Laboratory's Project Vanguard. The 75-foot tall rocket was part of the nation's earliest efforts to launch Earth-orbiting satellites. In 1959, NASA acquired Hangar S through an agreement with the Department of Defense and modified it for use for pre-flight processing. This is where the Mercury space capsules were received and tested. By the end of 1960, NASA referred to Hangar S as the nerve center of Project Mercury and home of the Space Task Group's Pre-Flight Operations Division, which had grown to over 400 technicians and contractors who prepared the Mercury capsules for launch. The processing of the Mercury spacecraft began with its arrival at the Cape Canaveral skid strip aboard a transport aircraft. It then was transferred to Hangar S for a capsule shakedown. The hangar contained all the necessary facilities, storage, and work areas required to prepare the capsule, including a white room. The spotless capsule checkout area was located in the northeast corner of the high bay. Across from the white room was an altitude chamber used for Mercury capsule environmental control system testing and verification in a space-like environment. The altitude chamber allowed engineers and technicians to ensure the capsule would not leak in space, and it also helped verify that the environmental control system, along with other equipment, all worked as designed. Hangar S was the location for final assembly and checkout of the spacecraft's escape tower. Placed on top of the capsule for launch, the tower was designed to pull the capsule clear of the launch vehicle in the event of a mishap on the launch pad or during ascent. It jettisoned from the rocket when a safe altitude had been reached. Once all assembly, checkouts, and testing were complete, the Mercury spacecraft was transported a short distance to Cape Canaveral's Launch Pad 5 to be mounted atop a Redstone rocket for suborbital missions, or to Launch Pad 14 for mating to an Atlas booster for the flights to Earth's orbit. While astronauts prepared for their eventual trips into space, a group of chimpanzees also were undergoing training to ensure humans could withstand the physical strain and G-forces during a rocket launch. The chimpanzees' training began at the Holloman Aerospace Medical Center in New Mexico, but their preparations were completed at Hangar S. The task of responding to lights by flipping a lever would demonstrate that the chimps could not only survive in space, but also perform tasks throughout the flight. The first chimpanzee to fly was named Ham. He launched on Mercury Redstone 2 on January 31st, 1961. During the 16-minute flight, the chimp flew 157 miles high and 420 miles downrange. After his recovery, a happy and healthy Ham proved the way was clear for an astronaut to follow about 4 months later. On May 5th, 1961, Alan Shepard became the first American to fly in space during a 15-minute suborbital flight.
So this was a very significant flight because the country needed this. The whole free world needed this flight at this time.
2 months later, Gus Grissom flew a similar suborbital mission aboard the Mercury capsule he named Liberty Bell 7. Throughout Project Mercury, Hangar S served as not only a spacecraft preparation facility, but it also was the base of operation for the astronauts after they arrived at the Cape, especially in the days and weeks just prior to launch. The astronauts often spent 12-hour days or even longer at Hangar S, rehearsing their missions in the procedures trainer, an exact mock-up of the Mercury capsule's interior. The simulations would help prepare astronauts and ground controllers for the real thing.
Climbing into that spacecraft and sitting on the top of the rocket was something we had simulated time and time again.
The hangar also was the location of the crew quarters located on the second floor. The astronauts slept, ate, suited up, and underwent medical examinations in the days and weeks before flight. But on occasion, astronauts described the crew quarters as simply austere and uncomfortable. A primary goal of Project Mercury was to determine how humans would respond to trips in the environment of space. So a regular part of preparations for launch were medical exams by the astronauts' medical team. Once the health checkup was complete on launch day, it was time for the complex process of donning the spacesuit that would protect the astronaut in the event of a capsule depressurization. The next step was the astronaut climbing into an apparatus with a seat similar to the Mercury spacecraft. Technicians then checked out the suit to ensure it would pressurize and work as designed. With the suit up complete, it was time to head to the launch pad. In the glare of television lights, the astronaut departed Hangar S for the transfer van. The specially outfitted truck would make the trip to Launch Pad 5 or Pad 14, where the astronaut would prepare for the final countdown.
5, 4, 3, ignition. 3, 2, 1, 0. Roger. Liftoff. Operating. We're underway. Roger. Reading you loud and clear.
3 days after John Glenn's historic mission on February 20th, 1962, President John F. Kennedy visited Cape Canaveral to see facilities such as Launch Pad 14, where Glenn lifted off. The presidential tour included Hangar S, where Mercury spacecraft were being prepared for future missions. And during a special ceremony outside the hangar, President Kennedy congratulated America's first person to orbit the Earth and those who supported his historic mission. Glenn's mission was followed by 3 more orbital flights by astronauts Carpenter, Schirra, and Cooper, each with longer missions and increasingly sophisticated capsule maneuvers and experiments. Following completion of the Mercury missions, the spacecraft would be returned to Hangar S for post-flight inspections. Key parts would be removed for study, so lessons learned could be applied to future designs. After the 22-orbit mission of Gordon Cooper aboard Mercury Atlas 9 in 1963, America's first human spaceflight program came to an end. Beginning the next year, Project Gemini would be NASA's bridge from the Mercury missions, learning how to meet President John F. Kennedy's goal to send astronauts to the moon. The first Gemini spacecraft also were processed for flight in Hangar S. The new program would allow humans to emerge from their spacecraft and begin to walk in space, as well as rendezvous and dock with other orbiting spacecraft. But as NASA began opening new facilities at the Kennedy Space Center on adjacent Merritt Island, Gemini processing moved to the Manned Spacecraft Operations Building, now known as the Neil Armstrong Operations and Checkout Building. The interior of the Hangar S High Bay was modified later in 1965 with the construction of a satellite processing area. These spacecraft included the Franco-German Symphony communications satellite and the agency's lunar orbiter spacecraft that mapped the moon prior to the Apollo missions, taking humans to work on the lunar surface during the late 1960s and early 1970s.
5, 4, we've gone for main engine start. We have main engine start. We have liftoff of America's first space shuttle. And the shuttle has cleared the tower.
As the space shuttle era began in 1981, work at Hangar S supported the new effort. During the shuttle program, many types of equipment, such as scape suits, were maintained and repaired at the life support facility inside Hangar S. The rubber-coated self-contained atmospheric protective ensembles were worn by technicians at Kennedy and Cape Canaveral for protection during processing activities that involved hazardous chemicals such as rocket propellants or in the event of a spill. Much of the operational area was used to maintain equipment associated with the retrieval of the shuttle's solid rocket boosters.
2, 1, 0, and liftoff, the final liftoff of Atlantis on the shoulders of the space shuttle. America will continue the dream.
Following STS-135, the final space shuttle mission in July of 2011, work inside Hangar S came to an end. Cape Canaveral's Hangar S was America's starting point for human space exploration. NASA at the Kennedy Space Center now has transitioned from a historically government-only launch facility to a multi-user spaceport for both federal and commercial customers. NASA's team on Florida's Space Coast continues to work to meet the nation's spacefaring needs for the 21st century. These advances will include the Orion spacecraft and the Space Launch System super rocket to take humans to distant destinations such as Mars and beyond.
We have been given the scientific knowledge, the technical ability, and the materials to pursue the exploration of the universe. To ignore these great resources would be a corruption of a God-given ability.
10, 9, ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running.
looks good.
We confirm that, 13.
Okay, we're going to start to pitch around to line up with the limb.
Pitch rate, 2.5 degrees per second.
Roger, Jack. 100 feet.
Okay, Houston, we have limb extraction.
Oh, we copy that, 13. Now you're off to the Fromar High.
This is the sound of Sputnik, the very first artificial satellite launched by the Soviet Union in 1957. In 1962, NASA realized that it would need a brand new communication system for the Apollo missions. Not only would the Apollo missions be going much further than the previous missions, they would also be communicating with 3 astronauts working in 2 different spacecraft, as well as sending telemetry and live television images back to Earth. They developed a system called Unified S-band, which could send telemetry, command, voice and television data using different frequencies but combined into a single antenna. This system would communicate with the Apollo spacecraft via fixed ground stations placed around the Earth. This would allow Mission Control to have continuous communication with the astronauts during the mission, apart from when the spacecraft curved around the far side of the Moon, where the signal would be lost until they reappeared on the other side 40 minutes later. During this time, the astronauts had to fire up the engines in a critical maneuver to make sure they reappeared on the other side of the Moon. If the crew had a successful burn, it would set them on the expected trajectory, meaning Mission Control knew exactly when they would regain communication with the Apollo 8 crew.
Apollo 8, Houston, over. Apollo 8, Houston, over. Houston, Apollo 8. Very complete.
We've got it. We've got it. Apollo 8 now in lunar orbit. There's a cheer in this room. This is Apollo Control Houston. Switching now to the voice of Jim Lovell.
Hi, I'm Chris, and this is NASA Now for January 11th, 2012. We've all seen these incredible images of astronauts in their spacesuits floating around in space. If you're anything like me, you've wondered how those spacesuits work. Well, today, we're going to learn about the complicated system that provides vital support to the astronauts during an extravehicular activity, also known as a spacewalk. Today's modern spacesuit is an amazing piece of equipment with technology that provides many vital functions. To help us understand the mechanics of the Portable Life Support System, or PLIS, is Antje Chambers, who works at the Johnson Space Center. Hello, Antje. Perhaps you can tell us about the backpack that we see on the astronauts when they're doing a spacewalk.
One of the key components of the spacesuit that doesn't get as much attention but is very, very important is the Portable Life Support System, which is usually the backpack that you see on our astronauts.
What does the PLIS do?
What the Portable Life Support System does is basically how the name describes. It provides life support. And so some of the key things that we need is breathing air. And so we provide oxygen to the astronauts. Main portion of the spacesuit. It gets recirculated. The astronauts, like everybody on the ground, breathes out carbon dioxide. It gets back into the PLIS. What the PLIS does is it scrubs the CO2 out of the oxygen and recirculates it into the suit. So that's one of the primary functions of the PLIS. It also provides the power to the spacesuit, usually via battery power.
Can you tell us about the lights that are on the sides?
You can see kind of these headlights on either side. The astronauts sometimes, if they're on a dark pass of the International Space Station, it gets dark. And so instead of having like a flashlight that they can hold in their hands, we typically like to put it on either side of the helmet.
What else does the PLIS, or Portable Life Support System, do?
It also powers a lot of the systems that provide status of the spacesuit. So the spacesuit is constantly giving down any information to the ground or Mission Control in Houston on, hey, this is what the spacesuit's doing, this is what pressure it's at, this is how much breathing air remains or oxygen remains into the system. And so that gives that description, and so we do need power for all of that.
Are there other functions of the PLIS besides power and oxygen?
The spacesuit, it has a layer inside it. We call it the bladder. And basically, it's almost like a balloon material. It's a urethane material. And this urethane material is, by design, not supposed to breathe. It's supposed to keep all of the breathing air, all the oxygen inside the spacesuit. But as a result, when the astronauts are working, it's almost like working out in a rain jacket. You get very hot very quickly and you start sweating. We don't want our astronauts to do that. And so we ended up putting a garment on the astronauts while they're inside the spacesuit. And this garment, it has about 350 feet of tubing that is stitched throughout that. And so what the PLIS does is provide cold water through that tubing, and that tubing takes all the heat away from your skin, so the astronauts are getting cooled.
What part of the PLIS do you work on?
What I work on specifically with both the EMU and the advanced spacesuit is a carbon dioxide sensor. The carbon dioxide sensor measures the amount of carbon dioxide that is going into the helmet of the astronaut or going into the main spacesuit portion of the astronaut. Carbon dioxide is a gas that we breathe out. Plants like it, humans don't. And so it's very important to put the carbon dioxide sensor kind of upstream of the helmet. And upstream means it's basically in the airflow before it reaches the helmet, so that we can know what percentages our astronauts are breathing.
43, 44, 43.5, 44.
When the three astronauts who go to the moon complete their final checklist before launch, they are ready for a 500,000-mile round trip. Their course is pre-planned and precise. And at their command, they have some of the most sophisticated devices made by man.
5, 4, 3, ignition detected. Transmitted 5 enter. Clock start, 5 enter. Thrust okay.
At liftoff, they are guided automatically until they reach parking orbit around the Earth. A small, complex computer in the Saturn V's instrument unit directs the rocket engines. They, in turn, push the launch vehicle into its proper orbit. But the astronauts are not alone. Their position is constantly being monitored and sent to the flight controllers at Mission Control in Houston. There, computers compare their flight with the one planned and revise the flight data.
Program 12. Trajectory confirmatories enabled.
The updated information is sent back to the command module, where it is stored in a small computer, the brains of the Apollo guidance and navigation system. This system makes it possible for the astronauts at any point in their lunar mission to pinpoint their position. In Earth orbit, they can use their sextant. An astronaut lines up a known star and a prominent landmark, and feeding his readings into the computer, gets his position back from the machine. As they leave Earth orbit and head for the moon, the astronauts are faced with another guidance problem, that of determining their attitude, or the direction the spacecraft is facing. The astronaut navigator finds a known star in the wide-angle telescope. Using a fingertip control, he changes the attitude of the spacecraft to bring the star into line. Once he has the star in position in the telescope, he moves the optical sextant. He lines the sextant up with the star and makes a reading. He must repeat the process with another known star so that he has two readings to give to the onboard computer. From this information, the computer determines the attitude of the spacecraft. Once the attitude is known, the 8-ball can be aligned. This device, similar to those used in airplanes, is stabilized with gyroscopes and connected directly to the computer. To the astronaut, it's the most important display next to the computer itself. When set, it becomes the primary guidance instrument in the spacecraft and is used to orient the spacecraft for the mid-course maneuvers. This information is vital to their mission, particularly for the mid-course adjustments they will have to make when their engine has to be accurately aimed for firing. To find his position in space, The navigator goes through the same kind of routine he used in orbit around the Earth. He takes a sextant sighting on a known star and on Earth's horizon. The computer, given this information, tells him where he is relative to the Earth. As the spacecraft approaches the moon, the same procedure, this time using the lunar horizon, tells him how close he is and his position in space. The 8-ball and the computer, armed with updated information from tracking facilities on Earth, direct the aiming of the spacecraft engine for retro fire to slow the craft down to orbit speed. The navigator can then determine the altitude of the orbit and the position of the spacecraft, just as he did around Earth, using a star and a lunar landmark in the command module sextant. For the actual landing, the lunar module uses a landing radar system tied into an onboard computer to tell him where he is relative to the actual landing spot. For the liftoff and the subsequent rendezvous, another radar unit feeds the necessary information to the lunar module computer, while the astronauts keep track of the orbiting command module with a sighting device on the window. The trip back to Earth is the opposite of the trip out. Star and moon sightings give the spacecraft's position. Mid-course corrections are made in the same way, using the 8-ball and the computer. The success of the first visit by Americans to the moon depends on many things. The rocket engines must perform without fail. The spacecraft systems must all operate reliably, and the men in flight and on the ground must be dedicated and able. And a major key to this success is the Apollo guidance and navigation system, telling the astronauts where they are and how to get where they want to go.
This is Launch Control. We have ignition start. 5, 4, 3, 2, 1. We have commenced. We have liftoff.
An Apollo mission begins as it ends in a searing mass of flame and heat. Project Apollo. Its mission, a lunar landing, exploration of the moon's surface, and the safe return to Earth of the 3-man crew. On an Apollo lunar mission, the final critical phase begins with fiery re-entry into the Earth's atmosphere. A camera on board an Apollo test mission vividly depicts the tremendous heat encountered by the spacecraft. For nearly 1,000 seconds, as the command module smashes into the atmosphere, it will be exposed to heat which can rise to over 5,000 degrees Fahrenheit. With only inches between their 75-degree cabin and the scorching exterior, astronauts returning from a lunar mission will be protected from the elements by a self-consuming ablative heat shield. During re-entry, the heat shield is exposed to sharply rising temperatures. The shield reflects a large part of the heat and dissipates the remaining heat by surface melting, decomposition during charring, and by cooling at the surface. The cooling is caused by the gases of decomposition as they percolate to the surface of the ablator. In this way, heat bombarding the heat shield is blocked from traveling back to the metal surface of the spacecraft. Developed and produced by Avco Space Systems Division in Lowell, Massachusetts, the ablative heat shield is the result of over 3 years of intensive research by the division. Actual manufacture of the heat shield begins with the arrival of the command module substructure from the Space Division of North American Rockwell Corporation, prime contractors for NASA's Apollo program. The command module arrives at Hanscom Air Force Base in Bedford, Massachusetts, aboard a specially designed plane known as the Pregnant Guppy. The Guppy is a converted stratocruiser utilized to airlift large shipments that cannot be carried by conventional planes. The module arrives from North American's Downey, California plant in 3 sections: the forward section, the main crew compartment, and the blunt aft section. Crates containing the 3 pieces are loaded onto large flatbed trailers and then transported to Avco. Because weight is of extreme importance in any space mission, technicians carefully weigh each component, make center of gravity determinations for each section, and perform initial measurement operations. After a special cleaning process, strips of fiberglass honeycomb, which form the base of the ablative heat shield, are fitted to the sections. The sections are then fixed to the spacecraft's stainless steel outer shell with a special adhesive. They are then heat bonded in a giant oven. The techniques for fitting and bonding the honeycomb were developed by Avco specifically for the Apollo mission. In all, the honeycomb consists of more than 370,000 individual and separate cells. Later, they will be filled one by one. There is no room for error in the bonding of the honeycomb to the substructure. To ensure uniformity of bonding, ultrasonic testing, utilizing sound waves, is performed all along the entire vehicle. The bonded sections are machined on a huge electronically controlled lathe. Because reentry heats will vary across the surface of the spacecraft, required thicknesses of the heat shield must also vary. After machining, a coat of gray primer is applied to all sections. The heart of the heat shield application comes with the insertion of the ablative material into the machined honeycomb. This is the section occupied by the 3-man crew during manned missions. Since conventional equipment could not handle the fibrous ablative material, Avco developed and manufactured special injection guns. The gunning operation is a meticulous one. Each gunner must constantly exercise intense concentration. All of the gunners are therefore specially trained and certified for the heat shield assignment. Because of its huge dimensions, the aft section is placed on a vertical rig so that the gunners can work on the entire surface simultaneously. The aft section is the first part of the spacecraft to re-enter the Earth's atmosphere. It must bear the brunt of re-entry heat. The 3 sections, now completely filled, are placed in ovens for curing. The sections are covered with rubber vacuum bags. Depending upon the section being cured, the process may require from a few hours to as many as 4 days. Because of the critical weight factor, it is necessary to grind away much of the ablative material in those areas of less severe heating. To achieve the varying and precise thicknesses required, 2 huge lathes controlled by computer tapes contour the heat shield sections with extreme accuracy. To verify the thicknesses of the heat shield, depth measurements are taken through holes left for that purpose. The holes are then refilled. X-ray inspection locates defective cells. To ensure that no voids, broken, or improperly filled cells exist, detailed X-rays are taken of all sections of the module. Areas which do not meet the exacting requirements are marked by the technician to be drilled out and refilled with ablative material. Despite its unusual size and shape, even the aft section is X-rayed, but in a different manner from other sections of the command module. Each section is inspected again and returned to the ovens for final curing. In the final steps, gaskets are installed to join all sections together. Clear high-gloss primer and a coat of white protective sealer are applied. Following final acceptance of completed vehicles by representatives of North American Rockwell Corporation and NASA's Manned Spacecraft Center, the sections are returned to Downey, California. In North American's clean room, the world's largest, an assembled Apollo command module outer heat shield is fitted over the inner crew compartment and mated with the rest of the spacecraft. The Apollo heat shield is now ready to protect the 3-man crew during the return trip from the moon. The command module is the only part of the entire spacecraft system that will complete the 500,000-mile trip to the moon and back. More than 300,000 scientists, engineers, technicians, and craftsmen from over 20,000 companies have committed their talents and efforts to Project Apollo, talents and efforts which are bringing ever closer this country's first manned journey to the moon.
With the 50th anniversary of Apollo 11 now here, it's easy to forget that the whole Apollo program was a groundbreaking succession of technologies, but one was essential to literally getting the whole thing off the ground. The Rocketdyne F1 engines would be the biggest, most powerful single-chamber rocket engines ever built, but there was a point in their development where they were so unstable it was looking like they might never get anything off the ground. So how did the F1 go from a dangerous failure to 100% reliable? The history of the F-1 goes back to 1955, when the USAF contracted Rocketdyne to build a very large rocket engine. Two were designed, the E-1 and the much larger F-1, for what was seen to be a need for future rockets to be able to carry much larger payloads like the emerging spy satellites. The E-1 was tested but dropped in favour of the F-1, but then shortly afterwards that was also dropped and development was shelved. After NASA was created in 1958 and the need for manned spaceflight had been boosted by the launch of Sputnik by the Soviets, NASA and Wernher von Braun, who had also been working on a lunar mission for a while, calculated there will be a need for an engine with 1.5 million pounds of thrust to lift the required payload for a lunar mission. So Rocketdyne was contracted to continue the development of the F-1. In its first full-scale test just before Yuri Gagarin's flight in 1961, a prototype F-1 produced 1.64 million pounds of thrust, proving the design. But even early on, the F-1 was exhibiting instability, something which wasn't out of the ordinary in engine development and would normally be fixed quite quickly. But in the F-1 it was different. Its instability would plague the engine for more than 7 years and would put the entire Apollo program in doubt if it couldn't be fixed. The F-1 was a relatively simple engine design, following in the footsteps of other Rocketdyne engines like the E-1, the Atlas MA2 and the H-1, which was used in the Thor and Jupiter vehicles. But its sheer size is where the F-1 stood out, and it's also where all the problems were concerned. Problems that were minor or not seen in smaller engines became major issues in the F-1. No one had ever built an engine this large, and some even said it wasn't even possible. And in the 1950s, rocket engine design was more of an art built on trial and error than hard and fast science. Computer modelling didn't yet exist, and theories derived from smaller engines didn't scale well with the F-1. In a rocket engine, the fuel, which in the F-1's case is RP-1, a highly refined kerosene, and the oxidizer, liquid oxygen, is injected into the combustion chamber, a barrel-shaped area under high pressure through an injector plate, which in the F-1 had 2,832 holes, each the size of a drinking straw. The job of the injector plate was to bring the fuel and oxidizer into the combustion chamber at the proper mixture ratio, pressure and spray pattern to initiate and sustain stable combustion. But in the F-1, because the combustion chamber was so large at nearly 1 metre across, some areas would start to burn hotter than others because of inconsistencies in the fuel and oxidizer mix. This uneven burning of the fuel created tangential spinning oscillations, which were called the racetrack effect. These acoustic pressure waves would oscillate around the chamber like a racetrack, hundreds of times a second, forcing the heat and pressure in the chamber to run out of control within milliseconds. This was termed rough burning and could create intense vibrations. The flame front could touch and burn the injector plate, and in the worst instances, the vibrations could literally shake the engine apart. This happened during a test on June 28, 1962, when the shock was so strong that the high-pressure fuel ducts ruptured, leaving it in an oxygen-rich operation which destroyed the entire engine. The problem was also highly unpredictable and could be triggered by almost anything from fluctuations in the turbo pumps to thermal shock from sudden temperature changes. The same engine on one test could experience little or no problems, and on the next test it would be so severe that it would have to be stopped. To tackle the problem, a team of 50 top engineers and technicians was set up to try and tame the F-1's combustion issues and set to work on the heart of the system, the injector plate. Here, they set about changing the angle and pattern of the fuel injector holes, each time testing the results. But by early 1963, 2 more engines had been destroyed and the problem was still there. So they came up with a radical plan to try and beat the random nature of the onset of the instability by creating instability on demand. That way they could methodically go through the problem on their terms. They decided to place a small bomb inside the combustion chamber. They would hang a small, heavily insulated black powder charge just under the injector plate, which could be triggered remotely. When the engine was fired up, the bomb was detonated and the shockwaves created the instability. If they could create a fix that stopped the effect of the bombs each time, they would solve the problem. To dampen down the wild oscillations around the combustion chamber, they placed baffles on the injector plate and changed the position where the fuels were mixed to farther inside the combustion chamber. Although this decreased the number of injectors available and made the engine a few % less efficient, it was a price worth paying. Hundreds of tests followed with 15 different baffle designs and changes to the injector angle and the point where the fuels were mixed. Some changes made little difference, others made it a bit better, but in the end they arrived at a point where the instability created by the bombs would die down within 100 milliseconds. After 3 years of work, they had finally arrived at a dynamically stable engine, and in April 1965, the first test with 5 F1s mounted on the Huntsville test stand took place. All 5 worked perfectly, producing a total of 7.5 million pounds of thrust for 6.5 seconds. Although they didn't know it yet, they'd cracked the problem, and from that point onwards, the F1 engines worked with 100% reliability. In time, 65 engines on 13 flights worked perfectly, but it had taken over 3,200 full tests during the entire program and 2,000 of those just to fix the instability. In the end, it was the most intensive and the most expensive rocket engine development program in history, without which the moon missions as we know them would probably have never taken place. The instability problems of the F1 were some of the most complex ever tackled in rocket engine design. But creating instability with small bombs to find the solution was just a measure of the ingenuity they used.
Okay, let's go there, Capcom on the hot fire. Okay, all flight controllers going around the horn, gonna go for undocking. Okay, retro, go. Fido, go. Guide, go. Control, go. Telcom, go. GNC, go. Econ, go. Surgeon, go. Capcom, we're go for undocking.
Armstrong, Aldrin, and Collins arrived at the moon on Saturday, July 19th.
When we did get close and we rolled out and saw it for the first time, it was a revelation. It was gigantic. It filled our entire window.
The next day, Sunday, July 20th, was landing day.
And a lot of anticipation. We finally come to the day, the moment that this is about to commence.
Landing on the moon was absolutely the most difficult piece of any Apollo mission, okay? Think about it as a controlled fall out of lunar orbit. The problem is, in this controlled fall out of orbit, you only have enough fuel for one try.
Capcom, we're go for landing. Altitude 4,200. Houston, you're go for landing, over.
The trajectory had been wrong. They were targeted into this inhospitable place. Then they had to fly over this area at a high forward velocity, then pitch up to slow down so that kill their forward velocity, and then start down like a helicopter. So now we're critical fuel state. And that's why the 60-second call was given, and then the 30-second call.
Then I really got nervous and was calling out 25 seconds of fuel left, and then 20 seconds of fuel. Oh, jeez.
Okay, engine stop. ACA at a descent. Mode control both auto. Descent engine command override off. Engine arm off. 413 is in.
We copy you down, Eagle.
Houston, Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
The landing to me was a great celebration. The nation was almost euphoric.
Well, it proved that the United States could accomplish tremendous goals if they worked together as a team.